Hello and welcome back. If you follow the channel, you know that we love repairing complicated vintage electronics. But modern electronic stuff fails all the time too, and is often more difficult to repair because it's undocumented, on purpose of course. So when I fix some modern electronics, I like to put out the video as a public service to help other folks out. And we always end up learning something new in the process. Today we are going to fight with our latest modern fail, my beloved Newall C80 digital readout on my lathe. In this case, it's even worse than undocumented, as Newall has gone to great lengths to keep the magical principle of operation of their position sensors proprietary. However, in their defense, and unlike most modern consumer electronics, this is industrial grade and superbly well built. It lasted for over 20 years with no issues. But recently the controller has developed this bizarre behavior, where it shows random numbers and is incapable of reading position. And I am not the only one with that problem, as the web is replete with reports of units failing in a similar way, with no one having a solution. The rub is that Newall does not support these anymore. Your only option is to buy a new version for at least $1,200 just for the display, and much more if you need to upgrade the sensors. Being from the 2000s, I was really expecting this to be a walk in the park, opening it up and finding a bunch of bad Chinese electrolytic capacitors in the power supply, not worth a video. But oh boy was I wrong. Not only it wasn't the caps, but I made it a whole lot worse from the get-go. And I was doing relatively well. I checked all the caps and everything was good, and I checked all the power rails and everything was good, and then I turned around and I showed Ken how good the power rails were, and I accidentally shorted these two pins, and that, my friends, shorts the 15 volts input with the 5 volts output, and that zapped the whole board instantly, of course. So now it does this, and I have no sometimes I have some random activity, but I have no processor activity. It used to light up correctly and display the firmware version, all that stuff. So I might have killed it catastrophically. There is an old processor that's an Intel-based controller. I have a spare. So the processor here is an Atmel TCS80251, which itself is a good old souped-up Intel 8051, a popular 8-bit microcontroller from the 1980s. Although the 8051 architecture is still alive and kicking, this version is an obsolete chip, so you have to get it from your shady eBay Chinese obsolete component seller. I believe that the chips being obsolete is one of the main reasons why Newall doesn't want to support this anymore. The chip industry has grown to have really short-term vision, which is a real issue as your designs get obsoleted in a matter of years or even in a matter of months. There are some ROMs, but of course there is a PLA, and that's encryption protected PLA, so you cannot get to it if you had to replace it. So I'll just try to replace the Atmel chip from my dubious Chinese vendor who shipped it in a non-ESD bag, and see if that revives it. If not, I think I am hosed. I would need to buy a parts unit. So I'm going to replace this. It's dead for sure. I had no processor activity, but I don't think that will be enough to revive it. Oh, it does! Okay. Well, we're temporarily back in business. And it has the same problem here that I had before. It's just showing random numbers. So phew, we got lucky with our clumsy probe slip incident. We apparently just fried our cheap processor chip, and all the rest looks as good or as bad as it was before. And I'm a bit mystified because there was no caps bad on the analog board, so I'm not sure what could cause that. A D2A problem? So likely the fault is in the analog section, which is not documented at all. So we need to concentrate on reverse engineering that. So far I have identified the main components on it. First, there are 3 power supplies which I checked and are all good. The big one is a switching power supply for the 5 volts used by the processor board. Don't short pin 1 and 2 while showing the circuit to your friends or you'll fry your processor. But the power supply chip is fine, thank you very much. Then there is a 9.4 volt linear regulator for the analog circuits and a low noise 5 volt linear power supply for some interface circuits between the processor and the analog circuits. They all checked good, as did their associated caps. Next is an ST202 ECN, which checks out as an RS232 driver chip. There is an RS232 port nearby for external communications with a computer, so that makes sense, and it has likely nothing to do with our problem, so we'll ignore it mostly. Then comes the first unusual chip, a MAX7426, 5th order elliptic low pass filter. Analog trickery probably awaits. The next one is a regular 74H14, a hex inverter chip. Then an LM339, a classic quad comparator. Then an LM324, a classic quad op amp. Then another surprise chip, actually 2 of them, the LM380s, which is a 2.5 watt audio amplifier. What are they doing in there? This is no stereo boombox amplifier. But this and the filter chip are a good hint that the sensors work at audio frequencies and that they need to be driven by some audio signal. So the good news is that there isn't that much on this board. It is still very mysterious and unusual though, so it's time to find some info on how the sensor works. And I could find just about nothing. Just a vague explanation from Newall that it worked with ball bearings and magnetics, which is all very mysterious. So I started to look at more recent Newall US patents, which themselves cited an ancient British patent from 1975. With a little help from my patent attorney at work, thank you John, I was able to dig out patent GB1513567, indeed awarded to Newall. And once I started to understand it, I thought it was plain freaking genius. The basic idea is to have a moving head with some transmitting and receiving coils riding over a non-magnetic tube that contains steel ball bearings touching each other. In figure 1, the transmitting coil is on top of the rod and the receiving coil is underneath. So the coupling between the transmitting coil and the receiving coil will be influenced by the position of the ball. But there is a catch. Using amplitude variations for detecting a fraction of a position over a ball is not going to give you the micrometer precision you need. Amplitude modulation is way too noisy. And that's where the genius of the final solution comes in, explained in figure 2. It's a combination of 3 tricks. Trick number 1 is to use not one but many transmitter-receiver pairs that are spaced by a little bit more than a ball diameter. So they create a vernier effect, and if you now compare the signals of the receiving coils, you get much better precision. The more the coils, the better the precision. Very clever. The next 2 tricks are even more impressive, using phase encoding and detection. They do this by exciting each transmitter coil out of phase with its neighbor by an amount proportional to the vernier displacement over the ball. In the figure 2 example, coil 5A is right at the edge of a ball, but 5B is a quarter diameter inside a ball. So you excite coil 5B 90 degrees out of phase from coil 5A. 5C is smack in the middle of a ball and gets driven at 180 degrees, and 5D is at 270 degrees. The next trick is equally genius and involves combining all the signals of the receiving coils. It's not shown in the picture, but instead of reading the received coils one at a time, you sum all the signals together. And although it's not clearly stated in the patent, I think what happens is that you get a continuously varying phase signal from 0 to 360 degrees as you move the head across the diameter of a ball. All you have to do is to measure the phase of the combined signal. Since it's now a time measurement, it can be extremely precise, particularly if your excitation is at low frequency, say in the lower audio range. At least I think that's how it works, and if we can repair the instrument, we'll be able to check if we guessed right. Okay, so I spent some time tracing the analog board and I'm starting to make sense of it, particularly on the excitation side. So apparently they generate some sinusoidal frequency that they feed to a coil in the sensor, in the magnetic sensor. They use a digital filter. By the way, so there's the digital filter, Schmitt trigger, comparators, op amp, audio amplifier, so not that much in it. Anyhow, this digital audio filter gets a clock from the computer, it gets a whatever kilohertz frequency audio signal in here, comes square wave, comes out, should be a sine wave filtered, then you can trace it, goes around the board, goes here, it's amplified by a unity buffer, then it gets to the audio amplifiers, there's one per channel, and it gets on this pin over here. So we should at least be able to trace if that's working. And then the return path, what I know is that all the signal fed back to the processor eventually goes through the hex gate. So if there is any random wiggles, I should see them over here. And if it's quiet over here, then it's probably not this board. So according to my diagram, a signal should come in, a clock should come into the digital filter. Oh, there it sure is. There it is, clock at 125 kilohertz. So that's good. And then the processor should feed it a square wave signal of some kind at lower frequency. There it is. Let's trigger on it. Oh, 1 kilohertz on the dot. So this should come out of the filter as a sine wave. There it is, 1 kilohertz sine wave. So that is all working perfectly. Is it making it at the output of my op amp, which should be over here? Oh, it is. It's shifted up, but it's fine. And then I suppose it's for the power amp. So the power amp should get it on the input over here. It sure does. Alright, and then it should come out amplified over here. Oh, there it is. Oh, yeah, it's amplified. Since I have no coil attached, it goes to the rails, I think. There we go. So that's working perfectly. The excitation part of the circuit is working. I have my 1 kilohertz excited coil. So my suspicion is that there's only 6 outputs, so it's going to be pretty quick. Output number 1, output number 2, nothing. Output number 3, nothing's at 5 volts. Number 4 at 5 volts, nothing. 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 That's concerning because I think the board is, so far as I can tell, it's quiet. It should report no signal. And it's doing all kind of weird numbers. So it might be on the digital board that the problem is, which would be harder to figure out because we don't know what the FPGA on the digital board does. Actually, that would be the next experiment, right? Connect it to a sensor, see if we see some signal when we move it, and that would tell us that that analog board, which I thought that was where the problem is fine. I think we're going to be left with a very difficult problem, is that there is something wrong in the computer board. I'm afraid the gate array as a rotten bit or something of that nature. And that's irreplaceable, except if you take it from another board. Actually, before we go into more debug, I noticed that it doesn't seem to keep memory of its config. So here it has a start screen, which it shouldn't have in the first place. But if I go into settings, setup, and configure it, and turn it off and turn it back on, it doesn't stick. Which tells me maybe the memory chip, it has a ferroelectric programmable ROM, the modern version of core memory. So why don't I replace that chip and see if it makes things better. So if I'm not mistaken, it's that little chip here on the side, this fellow right there. So let me change that one and see if it makes things better. No, came out. Alright, so suspect bad chip, and God knows if these are the real thing. They come from China. It's an obsolete chip. Okay, so we're gonna try that new chip in the right direction, I hope. Yes. Oh, okay, in its setup, so it behaves better. And we're going to try to set it up. Set up. So we have to set it for a lathe. Lathe. And it's a microsyn 10. X is diameter. Direction is 1 for X and is 0 for Z. Error off, because we're not correcting error. Addition, we're not adding serial. Single, that's the output, I think. Baud rate, parity none, 0 off. Oh, it's the 0 approach. Okay, we want that off. Tapers on the x-axis. Add delete function. No. Reset. No. Store. Stored. Aha! And now it behaves. So was that the problem? The ferroelectric memory. Let's turn it off. Try it again. Ha! Wouldn't you know it? So it appears to be that chip that did it. I'll remount it on the lathe and see if I get some signals. Okay, it's back on the lathe. All temporarily put in place. See if that works. Tja! That was it, man. Yeah? Thank you very much. So it's just a bad ferroelectric memory chip that just killed the whole thing. I'll be darned. So modern core memory ain't as good as old-time core memory. Okay, well, that saved me $800 or $1,000. And I hope it will save you the same amount too, because the replacement chip was like $5 or something like that for 5 of them shipped from China. Alright, so success. I am curious though how this works now. Right, so to satisfy my curiosity, I have made an extension cable. So it goes wee all the way down, all the way here, and I can look at the signal processing what the board does on the bench, and it does exactly what I thought it would. It's playing on phases. So you can see it. the indication changes as I'm turning my lathe. And if you go all the way on the scope back there and look at the green signal, its phase is changing. So the yellow signal is the excitation of the sensor, and the green signal is what it's getting out. And I totally expected that it gets a signal that which phases vary as it passes over the balls. And then on top of it, it just has a digital version of that, and that's what the computer board receives. So if you look at my reverse engineer schematic, it looks very complicated, but I cleaned up one channel and it's super simple. The signal comes back from the head, which is like the excitation signal but out of phase. Then it goes through an op amp, and then there is a comparator, and the comparator reference point is driven by the reference audio signal. It's a zero clamp followed by a capacitor that measures the average of the AC signal. And then this is a Schmitt trigger, and then that gives the square wave at each crossing. So here you have a sine wave, whee. Here you have a bigger sine wave, and here each crossing through the ref level will give you a square wave. Then it's given to the computer, and then you can see it how it's super simple, and the computer is just timing those signals. Then you can see, I'm going to go to the lathe and move them out of phase a little bit. There you go, something like that. So the excitation coil of the head is the yellow, and what comes out of the head is the green. That's after the Schmitt trigger. See, it just follows the green. There we go. See how the blue just follows the green, and then it just measures the difference in time between the blue and the red, and it knows your position exactly. It's amazingly precise and amazingly simple for what it is. Let's zero it. How long is a full phase? It's 10 millimeters, so there are 10 millimeter ball bearings inside that sensor rod. Just so clever. I am very impressed. And here you go, another modern fail, and I would have thought it would be a big bad cap or something bad in the analog portion, but no! It was a, well, bad processor because I killed it, that's my own fault. But it's a bad permanent memory chip. Newall tried to do good, not have any battery backed up CMOS chip, but have one that is supposed to keep its memory without any power at all. But that thing failed, which is really weird. Anyhow, it's repaired now.